So hello guys, most welcome to you all. So today we're going to talk about bipolar junction transistors, also known as BJTs. So these are basically PN junctions with two let me use this ink. So basically PN junctions with two junctions, I would say. That's why they're called bipolar. So we all know that a PN junction is formed by the materials used to adopt in certain ways and all that, so we shall get to talk about that. So basically, what are these? Why do we need bipolar junction transistors? So we basically need them because of the ability to control current flow by means of applied signals. So these transistors help us control the amount of current we want to supply to a particular device by using its control terminal, which is the base. So depending on whatever current or voltage you apply here, for in order to get a particular amount of current, we shall get a certain amount of current flowing from the collector to the emitter. That is for the NPN. Then here we would be having from the emitter to the collector as well. So for this case, majorly we're going to be focusing on most of the explanations I'm going to be doing are going to be focusing on the NPN transistor. We shall leave out the PNP since it's just the inverse of us doing the NPN. So basically the bipolar junction transistor has three terminals, as you can see here: the base, which is the control terminal, then you have the collector and the emitter. That's all. So these bipolar junction transistors can be applied in very many applications, such as switching circuits, current regulator circuits, voltage regulator circuits, amplifier circuits, and very many others. So let's come here. So how does this bipolar junction transistor work? So basically you should know that for what electrons to flow through a junction, there must be an applied voltage. There must be an applied voltage to give them the energy they need to move from this point across the junction to this point. That's all. So when we have our transistor with a zero voltage at the base, remember our base is the control terminal or control input terminal. So when you have zero voltage at the base, that means we're not biasing our bipolar junction transistor, and so the electrons here won't be able to get enough energy to cross this side. And so since that ain't possible, so nothing happens in our PN junction. So then if we bias this if we put a negative voltage instead of having this, then you have a negative voltage on the base relative to the emitter, what you would see is that we would be reverse biasing our PN junction. And what happens when you reverse bias our PN junction? The depletion region is going to increase. So you find that this region is going to increase here. Our depletion region will increase, and so there will even be a greater barrier for our electrons to even begin thinking of trying to cross this side. It will be harder for them to try to cross because the depletion region would have increased. So now let's talk about the forward biasing. So before I come to this diagram here, you need to know that whenever we're talking about, okay, so there are two analogies that we majorly use. That is that the conventional current flow, then there's the electron flow. So you find that, let me show you guys. If you have a battery plus and a minus, then I have a bulb connected this side. So you find that this direction of flow is considered the conventional current flow. Then this direction of flow is considered as the electron flow, because the electrons are flowing from here to here, but then the positives are flowing from the positive terminal going to the negative, and that is called a conventional current flow. So in most cases, when we're doing our explanations with these diagrams of bipolar junction transistors, we use the electron flow. The previous explanation I gave you guys was for electron flow, but then in most cases you find that when we're using these symbols of the BJTs, this is an NPN. I hope I told you guys that the direction in which the arrow is pointing is for the N, so you can just easily know that this is N, then the inside is P, then N. Let me just show you guys this. So as you can see here, this is going to be a N junction since it's pointing out, so it's N, P, N. I see. So our base is a P, then collector is N, and emitter is N. So here you see that it's pointing inside, so inside is going to be N, then the rest are going to be PP. So it's a PNP. That's how this comes, and that's how this comes. So as I was saying, when we're dealing with a symbol, we deal with conventional current flow. That's why we shall be saying that this is going to be IB, current flowing through the base, then this is emitter, I emitter, that's all. Then the collector current. These are all conventional current flows, but then as I'm going to explain to you guys, you're going to see that the electron flow is going to be in the opposite direction. So let's come this side. So now let's look at this. Remember, this is an NPN. You see here now, this is an NPN. So when we bias our voltage here positive, our base voltage positive relative to our remember our emitter is grounded, so our base voltage is greater than our emitter voltage, so we shall be forward biasing our PN junction here. So what happens? The electrons are given enough energy to move from this side to this side. Are you seeing? So now after they move this side, you realize that the designers always make that the base smaller, such that when these electrons come this side, of course some of them will be able to pass through the base terminal and go out, as you can see by these few arrows, but then most of them will be able to jump since the base is a very small let me show you guys here. So you'll have your N, then the P. The base region is very small. That's how it will be. So it's made small such that when our electrons cross this side, they can easily jump to the collector. So the rate at which they can easily jump to the collector depends on the magnitude of our base voltage. So the higher our base voltage, the easier it is for them to jump to the collector. So when we increase our base voltage here, the easier it is for these electrons to jump the other side. So the explanation I've just given you guys is for the electron flow. Now, as you can see by these arrows, they're saying that remember the electrons are jumping from the P to the N, but the conventional direction of current flow is IC, moving in the other direction. So even the emitter is going to be in this direction. So this is going to be conventional current flow for the emitter, not so. Then even this, remember the electrons are flowing down, so our conventional current flow is going to be up for the base. It's already shown here. So as they're showing by this arrow, they're saying that it's going to come like this. So here we shall just see that since all this, the current IC and the current IB are all moving in this direction and giving us IE, so it will be IB plus IC equals to IE. This is KCL, Kirchhoff's current law. So we see now how amplification of our current works. So now let's talk about, so there are basically three regions that describe that. So this graph here describes that the effects of the base current and the difference between the collector and the emitter voltage on the variation of the current flowing from the collector here. So we find that the saturation region, this saturation region here, our bipolar junction transistor operates at its maximum. So you find that the maximum current is flowing through the collector here. Here there will be a maximum current flowing here through the collector during saturation mode. So at that point, our transistor is acting as a closed switch. Then during the cutoff region, there's just little to no current. There's only the leakage current flowing through the base. So basically there is little to no current flowing here. It's only just a small leakage current flowing here, which is not enough to activate our transistor. So it's going to be an open switch. It's going to be acting as an open switch. Then in the active mode is where there is a near linear relationship between the currents, these currents here of the bipolar junction transistor. So what else do I need to explain to you guys? So now there are some very, very important rules when it comes to the working of a bipolar junction transistor. So for our transistor to work, let's consider this symbol of our bipolar junction transistor. So you have the base here, you have the collector, and you have the emitter. So for our transistor to work, the voltage, I told you guys I'm going to be working with an NPN transistor. So the voltage here, VB, must be greater than the emitter voltage, such that our current will flow in this direction also. So you must know that our voltage here must be greater than this. So in some cases you can find that this is grounded and you have a voltage here VB, or you can have a voltage here as well. But this voltage must be less than the voltage that you have here. This must always be greater than this by 0.7 volts or greater, or 0.6 volts or greater. So in order to activate our transistor, our voltage that we apply on the base must be greater than 0.6. That is when a current can be able to flow from our collector to our emitter. Else, if the voltage is lower than this, that means there will be no current, so it will be acting as what? An open circuit. So that is the major mode of operation of our bipolar junction transistor. So this equation here gives us the relation between IC, the current flowing from the collector, and the current flowing through flowing from the base. So yeah. So thank you very much, guys. This way I would like to stop because I'm seeing the video is getting too long. We shall go ahead and do more of this later. So I'm going to drop you guys the link to this and the name of the book that I'm using, and yeah, hope you guys also enjoy the read, and I'll always keep you guys updated on the summaries of what the information that I'm going to be getting, because yeah, I want to really understand these concepts of electronics, because that's where I really find my passion in, and I want to be very great at some point. So thank you guys for watching, and I hope to meet you guys in the next video where I'll be talking about FETs. Majorly I'll be talking about FETs, yeah, and the MOSFETs, JFETs, and very many other things, and the applications of the bipolar junction transistors and the other transistors as well. So keep up you guys. Ka-ciao.